Okay, folks, I hope this helps you out. We're going to analyze a basic well log according to Petty 1010. The first thing when you look at a well log, you should look at the very top to see what logs were run. On log number 1, we see in the lithology track 1, a spontaneous potential. We also see a hydrocarbon indicator. However, the hydrocarbon indicator is a computed log, often computed by an engineer who has been up for a day, 2 days, maybe more without any sleep. I don't put a lot of credence in the hydrocarbon indicator. We do use the spontaneous potential, and we'll talk about that in just a moment. The next, track 2, we see there is a resistivity curve, or 2 resistivity curves. We use the deep induction curve for our interpretation in Petty 1010 because the deep induction curve measures the resistivity of the fluid in the formation in the virgin zone, in the zone that was not commingled with our drilling fluid. In track 3 of log 1, we see the interval transit time. This is essentially a sonic or acoustic tool which measures interval transit time as it goes through the formation. Log 2, in track 1, which is our lithology track, we have a caliper which measures the size of the hole, and we have a gamma ray. The gamma ray is very similar to the spontaneous potential. Both will help you and help determine where sandstone is or where shale is. And remember, in Petty 1010, we're only dealing with 2 rocks, sandstone or shale. The spontaneous potential is the result of an electrical potential which is created by commingling of drilling fluid with formation fluid. The gamma ray measures the natural gamma radiation of the Earth. And since shale formations tend to hold radioactive material, where sandstone formations, the heavier radioactive particles tend to be washed out, the sandstones will read a lower gamma ray reading than will the shales. And then in track 3 and 4 of log 2, we have what's called the porosity index. We have 2 curves, a compensated formation density porosity and a compensated neutron porosity. Okay, let's get started with analyzing the log. First, we'll look at track 1 of log 1, the spontaneous potential. And we'll draw a line as indicated by the gold line across the top of the sands. We will assume that anything touching the gold line is considered to be 100% sand. And then we'll draw a green line. The green line will indicate shale. Any line touching the shale baseline will be considered 100% shale. And of course, anything in between the green and the gold line will be a mixture of sand and shale. Track 2 of log 1 is a resistivity track, and track 3 is the interval transit time. Let's draw a line across the top of our zone of interest. The black line indicates the top of the sand. The second black line indicates the bottom of the sand. Now, in this sand, it is quite evident by looking at the resistivity curve, the deep induction, remember, that we have some type of hydrocarbon in the formation. However, the entire formation is not a hydrocarbon formation. We have hydrocarbons at the top and we have water at the bottom, as indicated by the low resistivity reading. Therefore, as we said in Petty 1010, anything above 1 ohm meter for the deep induction curve is considered a hydrocarbon zone. The yellow line indicates the bottom of the hydrocarbon zone. In reality, it is possible to have a much lower resistivity reading and yet have a productive formation. In some cases, you might have dispersed clays within the sandstone, dispersed clays which hold water, thus causing the resistivity reading to be much lower than we would expect. This would be called low resistivity pay, and you'll learn more about it in Petty 3036, the course you take in well logging when you're a junior. Now, when we look at the resistivity, though, in the zone of interest, there's a hydrocarbon zone, I notice that zone, which is real high, and then the zone decreases. So the first thing we need to do is to calculate water saturation. Water saturation is the square root of RO divided by RT. RT is the formation true resistivity in and is the reading from the deep induction curve in the zone of interest, or the target zone, as I like to say, RT, target zone, zone of interest, true resistivity. RO is a reading from the deep induction curve in a clean, non-shaly formation, fully saturated with water. So, again, let's set our log up. Look at the top of the sand, the bottom of the sand, and the bottom of our productive zone. Now, when we're looking at the sand, we do notice the high resistivity reading in this zone of interest is 30. However, throughout the entire formation, the mean average of the deep induction is not 30. So what we have to do is we have to calculate two different zones within this zone of interest, this hydrocarbon zone. Zone 1 would be indicated by the red line, and that has a 30 ohm meter reading. Zone 2 is indicated by the purple line, and it has a 2 ohm meter reading. Therefore, let's calculate water saturation for each of these zones of interest. But first, in order to do that, we must determine RO. RO is in a clean 100% wet zone, and we calculate, or we measure, RO to be 0.3. Are we sure that that's 100% water? Well, I'm fairly confident that it is, and if you go down the log and you look at the two zones of interest further down the well, the RO from those formations, which we assume to be 100% wet, would be about the same, would also be about 0.3. So 0.3 seems to be a good number for our RO. So again, water saturation equals the square root of RO divided by RT. And this would give us for zone 1 a water saturation of 10%, and in zone 2 a water saturation of 39%. Remember, the 10% water saturation in zone 1 might be water that we will never be able to produce. It might be the result of wetting water. However, the reservoir engineer needs to calculate it and to account for it when determining total reserves. The next step to evaluate this log is to determine the porosity of the zone of interest, the zone that we found to have hydrocarbons. Porosity equals delta T minus delta T matrix, divided by delta T liquid minus delta T matrix, where delta T liquid and delta T matrix are the transit times in the pore, liquid, and rock matrix respectively. The sonic log investigation is limited to the invaded zone. The mixture of liquids in the rock pores is usually assumed to have a transit travel time of delta T liquid of 189. Selection of the matrix level time, delta T matrix, is based upon the knowledge of the lithology of the section logged. Commonly used delta T matrix values are as follows. Sandstone, 55.5 microseconds per foot to 51 microseconds per foot. Limestone, 47.5 microseconds per foot, and in dolomite, 43.5 microseconds per foot. In the unconsolidated sands found in South Louisiana for petty 1010 classwork tests, for delta T, use 55.5 microseconds per foot. If we were looking at a formation in Colorado or Wyoming where the sandstones were well cemented together, we might use 51 microseconds per foot. Again, now we looked at the log, and what we need to determine is the porosity in the zone of interest. If you look at the zone of interest where the hydrocarbons are, we see a reading which is fairly close to about 100 microseconds per foot. The interval transit time, track 3, goes from 50 to 100 to 150 microseconds per foot. We know, however, that the sonic log or acoustic log is calibrated in water. And if this happens to be a gas formation, it's going to give us a quite erroneous reading. If it's a formation containing oil, the reading would be erroneous, not quite as bad as if it were in gas, but erroneous nonetheless. So we go down to the water zone, probably where we pick RO from to determine the interval transit time. However, when looking at our log, our sand, our formation that has the hydrocarbons, just below it where we did pick RO from, we notice that we're getting a very inconsistent reading from the interval transit time from the sonic or acoustic log. This looks like it might be due to shell stringers. It also might be due to the tool bouncing around or some unexplained noise. Therefore, I prefer to go down to a sand a little bit further down the formation, as indicated by the two sands in red, and select my interval transit time from these sands. I am making an assumption that those sands are homogeneous to the sand in the hydrocarbon bearing zone. We will only know that if we shoot sidewall cores and have the cores analyzed to ensure homogeneity. Therefore, we can calculate porosity from the log. Again, porosity equals delta T log minus delta T matrix divided by delta T fluid minus delta T matrix. Delta T log is 90 minus delta T matrix 55.5 for unconsolidated sandstones divided by 189, which is delta T fluid, a constant, minus 55.5 delta T matrix. And the porosity equals 0.258426. Of course, even though our tools might be very sophisticated, we're making assumptions. So round off the porosity reading. we have approximately 26%. Now, the next thing we need to do is to look at track 2, look at log 2, look at track 1 to help us further analyze this log. Right now, we know we have a hydrocarbon producing zone. We know how many feet of production we might have, but we don't know if we have gas, if we have oil. And so we're going to look at the porosity log, log 2, to help us determine that. Again, now, we do not have an SP, but we do have a gamma ray. And with the gamma ray, we will draw a curve through the top of the sand and a curve through the bottom of the sand. And then we'll look at the porosity curves, and we'll remember the rules that you were taught in class. When there is separation, such as in the area designated as shale, where the neutron's reading high and the density's reading low, that's a good indication that we're in shale. When the two logs come together, that's a good indication that we're in a liquid. Do we know if it's a oil liquid or water liquid? No, we don't. The only way we know that is by looking at our figure of water saturation. And when the two logs separate, when they invert, when the neutron reads low and the density reads high, they crisscross from the normal shale reading, we know we're in a gas. So if we were to look at our formation, we would realize the top of that formation has gas, a gas cap. The middle of that formation is liquid, and we had calculated the water saturation to be only 39%. Therefore, it looks like we have oil, with some water, of course. And the bottom zone, again, would be water. Well, one other thing I'd like to point out is take a look in track 1 of log 2, and you do have a caliper. And if you notice in the sandstones, the caliper's pretty much engaged. In the shales, the caliper's washed out. So if I were to ask you, if I were to give you these logs and ask you, at what formation are we in at a particular depth, tell me all of the indicators that you have, you would start by looking at the spontaneous potential. You would look at the resistivity. You would look at the interval transit time, which tends to read high in shales. You would look at the caliper. You would look at the gamma ray, and you would look at the neutron intensity. For each of these curves can give you some indication as to what type of formation, what type of lithology you might be in.